Hi everyone, I present this work together with Ad Stoffelen from the Royal Netherlands Meteorological Institute and together with Marcos Portabella from the Barcelona Expert Center. During this presentation, I will introduce you the context of the work, then the motivations that pushed us to go through this study. I will show you our preliminary results and conclusions and some proposals for future work. So we did this work when I was at KNMI from 2017 to 2020, carried on a project, a EUMETSAT fellowship. The project name is GNSS, Observation Operator Development and Impact Evaluation, whose aims were the setting up of a quality control scheme for both TechDemoSat-1 and Cygnus DDMs, the development of an observation operator, and then to evaluate the impact of GNSSR-derived winds and weather forecasts. People that want to know more about this project can refer to the link at the bottom of this slide. So, our motivations. Basically, GNSSR winds have low impact on weather forecasts. The main reason is that the bistatic radar configuration of GNSSR makes the radar cross-section less sensitive to winds higher than 7 meters per second, very low sensitivity. This is an intrinsic problem that does not have any solutions, but if you want to reduce the noise on the sigma naught measurements, you can undergo an intercalibration procedure that is called track-wise calibration, and you can probably apply a multi-look approach instead of a single-look approach. And this is what we want to demonstrate in this presentation. So while carrying on this project, we demonstrated that both TechDemoSat-1 and Cygnus DDMs are affected by distortions that are caused by the inaccuracies on the estimation of the specular point. You can get rid of these distortions by resampling the DDM by means of a Shannon interpolation. People that want to know more about these details can refer to the papers listed in this slide. For what concerns the stir processing, what is that? So, first of all, on the left plot of this slide, you have the so-called DDM, so a delayed Doppler map, which is represents a typical DDM acquired over the sea surface, where you can recognize the typical horseshoe shape. On the right side, so on the two plots, on the bottom right and upper right corner of this slide, you can see the projection of the isodelay and isodoppler lines, which are respectively depicted with the ellipses and the straight lines. And then you have overimposed also a bullet which represents your stir point. So basically what happens is that this target point is sounded several times by a consecutive set of DDMs. So up to n times, in the case of Cygnus, this n is equal 9. So the idea of the stir processing is that of exploiting these n looks by optimally averaging this information in order to reduce the noise on the measurement. So you can implement this, at least as we implemented that, in two different ways. So we consider a target area around our stir point, or we consider only the stir point. So in the first case, you have that the corresponding cumulative Woodward ambiguity function is depicted on the upper right plot. Otherwise, in the second case, you have that the Woodward ambiguity function is much thinner, smaller. Of course, in the first case, which is a multi-beam approach, you have that your target area is projected onto the DDM in the black framed beams, while in the second approach you have that your target point is projected on the red framed beam. In order to have an idea of how this stir processing works, please look at this video, so this movie. So while the sensor is going on, your target area is sounded in different parts of the consecutive DDMs. And of course, if you apply the multi-beam approach, you will have a larger area than with respect to the single beam approach. Effective sounded area is different, and you can see here on the right side you have the effective sounded area with the single beam approach, while on the left side you have that one for the multi-beam approach. Of course, you have here two different curves, which are the cyan and magenta lines, which represent the -3 dB and -10 dB respectively, effective sounded area. And while your target area is depicted with this red dashed line. So what is the processing chain? We first of all resampled the DDM with the Shannon interpolation in order to get rid of the distortions caused by the specular point inaccuracies. Then we mapped the stare point or the stare area onto the DDM. We compute a sigma naught for each of the looks. Then we detrend the sigma naught profile for all the looks in order to get rid of the trend that is caused by a different local specular reflecting angle. And then we compute the sigma naught for the entire set of looks by means of an averaging procedure, and then we calibrate the measurements by means of the NOAA scale factor. So we apply a track-wise intercalibration, which is described in the paper that you can see at the bottom of this slide. So we used a data set relating to the period from June to August 2017. We collocated the CYGNSS information with the ECMWF forecast and with the scatterometer measurements of the ASCAT mission. Then we did constrain the collocation with the following special temporal constraints. So the acquisition time has to be within 40 minutes, while the maximum allowed distance is 25 kilometers. And then we apply a quality control scheme, which is the logical end of the quality control applied on CYGNSS DDMs by the mission, the mission group, then the quality control applied by means of our scheme, then the quality control on the scatterometer measurements, and the quality control of the K factor provided by NOAA. And with these constraints, we have a total of almost 400,000 triplets. So I will show you a sensitivity analysis with respect to the specular point-induced distortions and with respect to the number of looks. We focus on the 9 versus 5 looks, and then we will compare the results of the reduction of the noise with respect to the DDMA Gleason. We call that this way. DDMA stands for DDM area, which is the single look measurement, which is provided by CYGNSS on the official portal. But this DDMA is computed according to the paper that you can see here. So the main problem, and it is important to stress this factor, is that the DDMA provided on the CYGNSS portal has been recalibrated, but only the DDMA and not the entire DDM. We are interested in the DDM, so we need to do a fair comparison between our results and DDMA that comes from the same DDM. This is the reason why we did apply the algorithm presented here. And another important aspect is that the K factors provided by NOAA are fitted on the DDMA provided by CYGNSS and not on the one described in this paper. This is a time series which shows the sigma naught versus the time index. The sigma naught y axis is reported on the right. On the left of this plot. Overimposed to these plots, you can see also the black curves, which represents the the wind speed with respect to the time index. For what concerns the sigma naught, you have here three curves. So respectively, the DDMA, computed according to the paper from Gleason, the specular derived, the step processing derived one with the one beam approach and the multi-beam approach, respectively in red and green. What you can see here is that the curve of the sigma naught obtained with the multi-beam step processing is smoother with respect to the one obtained with the one beam approach, which on its turn is smoother than the DDMA. So what you retrieve here is that you have a reduction of noise. Another important aspect in this plot is that you can see an anti-correlation between the sigma naught and U. This is expected because as it is a epistatic radar configuration, what happens is that the lower the wind speed, the lower the sea state, the higher the echo towards your antenna. So for what concerns the sensitivity to the specular point-induced distortions, we see that if we apply the Shannon interpolation, we have a reduction in noise. So for the single beam, you have that the reduction is in the entire range between 0 and 20 meters per second. The same happens for the multi-beam approach, but the first range, so from 0 to 2 meters per second. But in the second case, so for the multi-beam approach, the reduction of noise is lower than in the single beam approach. This is of course expected because in the multi-beam you have an averaging procedure which reduces by itself the noise. For what concerns the sensitivity to the number of loops, here we compare the reduction of noise obtained with 9 loops with respect to the one obtained with 5 loops. With the multi-beam step processing approach, you have that the reduction of noise is effective on the entire range from 0 to 20 meters per second, while for the single beam approach, you have that the reduction is effective only up to 12 meters per second. If we compare the reduction of noise against, so the measurements against the DDMA, we experience a reduction of noise for both the approaches, which is consistent in the entire range from 0 to 20 meters per second. What is important to stress here is that while the reduction here is about 5%, in the track-wise intercalibration reduces the noise by a 20% factor. So this is to say that the step processing will give a second order effect with respect to the intercalibration procedure, but this second order effect is not negligible, so it is suggested to apply a step processing approach. So our preliminary conclusions, no corrections are effective, but they should be tailored for our purposes on the entire DDM and not only on the DDMA. The DDMA, which is provided by the Cygnus portal, is not consistent with the one that we used here and that comes from the paper from Gleason et al. And in general, it performs better than the DDMA that we used here and also the step processing that we implemented here. The distortion removal impacts both the step processing approaches presented here, even if it's a second order effect. And we have verified that the higher the number of loops is, the lower the noise on the sigma naught is for both the step processing, even if in the case of the multi-beam approach, we have that the reduction of noise is effective on the entire wind speed range between 0 and 20 meters per second. We have a good improvement in low wind speed ranges. So for future work, what we want to do is recalibrating the track-wise scale factors for the entire DDM and not for only the DDMA, and retrieve the wind speeds for both the step processing approaches. So if you have any questions, please contact me at this email address, and many thanks for your attention.